Hello, geometry students. Welcome to this lesson on coordinate proofs. This is going to be another lesson on another type of proof, okay? And I know these proof lessons can be a bear, but I'm going to say this about coordinate proofs. A lot of times what the textbook is looking for with the problems for these at least is just for you to use the coordinate proof to get an answer, not to go through the entire proof with all of the steps and reasons and statements. I'm going to show you how to do that with coordinate proofs in this lesson because there's a couple that say prove this, prove that. Okay, when we are told to prove, I am going to go through the proof so you can see what it looks like when it's all spelled out. But I'm just going to tell you, a lot of times when we run into problems on coordinate proofs, it's just they're looking for an answer, not the entire proof. And that should be a relief. All right, in this lesson, we are going to be learning about coordinate proofs, and we're going to start by talking about the best way to put your figures onto an XY coordinate plane. The best way to do that is to make sure you try to line up sides of your figures with the X and Y axes. Okay, so a right triangle will have two of its sides lined up with axes. One side can be on the x-axis, one side can be on the y-axis. If you don't have a right triangle, like this triangle in this figure right here is not a right triangle, you can't get two of its sides on axes. So what you'll have to do is choose the best side to go on an axis, probably one that makes the rest of the triangle symmetrical in either the y or the x dimension. So because this triangle was put so its long side was on the x-axis, now if I cut it through its other vertex that's sticking up, it's going to be symmetrical across that vertex, and that's just going to make it really easy to work with too. So the goal is we're trying to put figures in an arrangement that makes them the easiest to work with. Essentially, one vertex is always going to go on the origin, and then we're going to orient the triangle or the quadrilateral or whatever it is. We're going to orient it so that it's going to be like as many vertices as possible go along other axes, or it's symmetrical in a key way, or just we've got to graph the best we can to make it work. Now, the reason we want to put things on axes is because you'll notice some of the coordinates are zeros if they're on axes, and zeros are really easy to work with in calculations. That's the reason why. All right, let's get started on this. Now, I've actually already got a lot of this work pre-done. We're going to work out E together on this coordinate plane when we get there. Letter A says to place a right triangle with leg lengths of 2 and 6 on the coordinate plane. So its legs are on the x-axis and the y-axis. Ooh, smart. If its legs are on the x-axis and y-axis, that means that one of the coordinates of each point is going to be 0. And the coordinate of the point that's on the origin is going to be 0, 0. And those will be really easy to work with if I do calculations. Label the vertices as their respective coordinates. Well, that's this triangle right here. Notice that I've lined it up so that one of the legs with a length of 2 is on the x-axis. The other one's on the y-axis with a length of 6. And these are what the coordinates look like. Notice all those delicious zeros. All right. Letter B. Prove that triangle JKL in this figure is an isosceles triangle. So the first thing I'm going to do is I'm going to go back and review the definition of isosceles triangle. I'm going to realize that an isosceles triangle has two congruent sides, and that means that it also has two congruent angles. Now, I don't need to prove that it has two congruent sides and two congruent angles. It's enough to prove one or the other. What are we going to be able to prove from a coordinate proof like this? Well, with coordinate proofs, I'm not going to be able to prove anything about the angles, but I can prove things about the sides. So let's just take a look at how we can do this. So I know that I have triangle JKL with J at 0, 0, K at 1, 1, and L at 2, 0. That's my given, is the coordinates of all 3 points from my diagram. I don't have anything else. I don't have any arc marks. I don't have any tick marks on the sides. No congruency marks anywhere, just this. But I can prove congruency from this because I do have a formula known as the distance formula that can be used to calculate the lengths of the sides. JK can be calculated by doing y2, it's the x2 minus x1 squared plus y2 minus y1 squared. x2 is 0, so it's going to be 1 minus 0. y2 is 0. Hey, isn't that convenient? That's because this first point is at 0, 0. It makes it really easy to calculate with. So it's just going to be 1 squared plus 1 squared is 2, and then I have to take the square root of that. The length of jk is the square root of 2. Now I can use the distance formula to find KL in the same way. So I'm going to have x2 minus x1, x2 minus x1 squared. That's going to be 2 minus 1 squared is just 1. Plus y2 is 0 minus y1 is 1. 0 minus 1 is negative 1, but negative 1 squared is just positive 1. So here again, I have 1 plus 1 squared root of 2. Oh, did I just prove that JK and KL have the same lengths? I sure did. I can say that because JK is equal to square root of 2, KL is equal to square root of 2, and then by the transitive property of equality, if two things equal the same thing, they're equal to each other. Next thing I do is I'd say the segments are congruent. I should probably put segment symbols over the top of these, so it's segment JK is congruent to segment KL. And wait a second, I just proved, because an isosceles triangle has two congruent sides or two congruent segments, I proved that this has two congruent sides, so therefore it is an isosceles triangle by the definition of isosceles triangles. All right, letter C. Now we're going to get to some abstractions. Instead of putting specific side lengths on, I'm going to put a variable side length, two variable side lengths. I'm going to make this triangle look just like my first one. It doesn't really matter. I'm going to try to make it look like whatever the problem describes as specifically as the problem describes it. But if the problem doesn't describe it very specifically, I get to make the diagram however I want. And later on, if I figure out A was way out of proportion compared to B, then I could fix it later, or I could just recognize that I'm out of proportion. But anyway, all I know is this is a right triangle. So I'm just going to copy my previous right triangle, and instead of 2 and 6, I'm just going to put A and B, and I don't know what A is or what B is. I probably shouldn't even have all these lines in the background of this graph. I probably should just have one line and say that that line is B, and I don't know what the scale is of this thing. The same with A. I don't know if this is at 2. It probably isn't, but I'm just going to put it somewhere. I have to put it somewhere, so I'm just going to put it here. This is what this would look like if I use variables for my coordinates instead of using specific numbers. All right, letter D. Prove that figure TUVW is a parallelogram. Well, first of all, I'm going to review the definition of parallelogram. I looked it up, and a parallelogram has two sides that two opposite sides, both sets of opposite sides are congruent. I know that both pairs of opposite angles are congruent, but that's not very helpful on a coordinate plane. But I do know that both pairs of opposite sides are parallel to each other too. And I think that's going to help me prove that this is a parallelogram. So let's see what we can do here. Now, the first thing I would state, and I'm not going to state it here because of space considerations, but I would write this down if I were actually doing the proof. I'd write parallelogram UVTW has points U negative 35, V 35, T 00, W 60, and that's given. That's my given. Okay. Now I'm going to work with that given. I'm going to use the distance formula for UV, y2 minus x2 minus x1 squared between points UV plus y2 minus y1 squared. Y2 minus y1 is just 5 minus 5. So that one's going to be 0. So I'm just going to have 3 minus 3 minus negative 3. 3 minus negative 3 is 6. 6 squared is 36. And then the square root of 36 is back to 6. Okay, that's UV. Now let's do the opposite side. Let's do TW. 0 minus 6 plus, I'm going to square that. Let's see, did I do that right? X2 minus X1. This should be 6 minus 0. But that's okay. It would have been the same thing anyway, but we'll do 6 minus 0. I'm just going to correct that. Plus 0 minus 0. And again, that's the product of choosing good points for my parallelogram. So the square 6 minus 0 is 6. 6 squared and then the square root of 6 squared is just going to be 6. So I've proven these opposite sides are equal. What about my other set of opposite sides? So they, by the way, I'm going to use the transitive property of equality to state that those are equal because both sides are equal to 6. That means they're equal to each other. We're going to do the same thing with UT and then with VW. UT, I'm going to say x2 minus x1. That's going to be 0 minus negative 3 or positive 3, right? 0 minus a negative 3 is 0 plus 3 plus 0 minus 5. And I'm going to square both of those. 3 squared plus 5 squared is 9 plus 25, which is 9 plus 25 is 34. So this is going to be a square root of 34. That is not a pretty number, but it really doesn't matter. All I need to do is prove that the other opposite side is the same length. And sure enough, when I plug in the values from its coordinates, it does. So because these both have a length, the square root of 34, they're equal to each other. And then I can say that opposite sides are congruent by the definition of congruent segments. That's half of my proof that this is a parallelogram. But I also need to prove that opposite sides are parallel. To do that, I need to use the slope formula. So the slope formula is y2 minus y1. I'm going to use this for uv. y2, 5 minus y1, 5 over x2, 3 minus x1, negative 3. The x's don't really matter here. Other than that, they're not 0. 3 minus negative 3 is 6. But my numerator, y2 minus y1, 5 minus 5 is 0. So that means this has a slope of 0. The same is going to be true for the opposite side, TW, which is also 0 over 6, which is just 0. 0 is the slope, okay? So I've proven that those opposite sides have the same slope. And then I'm going to do the same thing for UT. Y2 is 0, Y1 is 5. So it's going to be 0 minus 5 over 0 minus negative 3. 0 minus negative 3 is just plus 3. So it's going to be negative 5 over positive 3 is the slope of UT. And the same is going to be true for VW, except this one's going to be, oh, look, it's almost exactly the same. The only difference is instead of 0 minus negative 3, I do 6 minus 3 is 3. So it's going to be negative 5 over 3. I've proven that these opposite sides have the same slope, and that lets me say that opposite sides are parallel according to the postulate 17, the parallel postulate. And therefore, I could say that TUVW is a parallelogram by the definition of a parallelogram, which says it has to have opposite sides congruent and opposite sides parallel. I've proven that both of those are true from a coordinate proof.